Good morning. Thank you all for coming. My name is Raghav Al-Ghazi and this is Yaroslav Gutman. And we are from Aalto University, and today we're presenting self-supervised end-to-end ASR for low resource L2 Swedish. So the context of this work lies in the production and development of automatic speaking assessment for both spoken Finnish and Swedish. So, as you may know, developing speaking assessment or automatic speaking assessment is a multifaceted process that all or some of which is reliant on the development of automatic speech recognition system, and after which there are several components to evaluate either lexical accuracy, grammatical diversity, and pronunciation and fluency. So, typically, L2 ASR is developed in a conventional ASR fashion where there is a customized engineering solution required for both pronunciation modeling and language modeling. On the other hand, it would be an end-to-end ASR could eliminate the laborious engineering effort, but the problem is it requires a lot of data, and that might not be always feasible or available for languages such as Finland, Swedish, or Finnish. But to this end, self-supervised method allows us to leverage untranscribed speech and allows us to build very rich contextual models that can be implemented into an end-to-end ASR strategy.
To the best of our knowledge, we're the first to develop L2 low resource ASR in completely end-to-end fashion without applying any external language model or pronunciation dictionary. We also demonstrate that the self-supervised deep acoustic models pre-trained on large amounts of untranscribed speech are able to provide competitive performance on L2 Swedish when using only a small amount of labeled data. Finally, we show that the pre-training data doesn't necessarily have to be L1. It can be out of domain, it can be L2, or it doesn't necessarily have to be L2, it can be L1 or even from other languages. So for our experiments, we collected Swedish speech data from Finnish high school students. In total, there were 341 Finnish high school students. The students were asked to answer different questions, different tasks, such as general speaking situations, image description, or share an opinion on some specific topic. In total, there were 26 different tasks to answer, and the whole size of the dataset is 4,777 recordings, or roughly 19 hours of speech. The responses were recorded in normal classroom conditions, so in some recordings there might appear other student speech or background noise. For testing purposes, there is a manually composed test set of 57 recordings from 7 different speakers.
So the core model of this, the acoustic model or the self-supervised acoustic model that we are using here is developed by Facebook AI group, which is called Wave2Vec2. It's a rigorous transformer coupled with the CNN architecture that's trained in a contrastive loss manner. So the model is trained. You could use this to pre-train it on a labeled data or untranscribed speech, and then it can be deployed on an end-to-end ASR strategy. So we fine-tune this model on our data and by randomly initializing classification layer to predict 35 output tokens, and we optimize that using Adam, or we optimize the CTC loss using Adam Optimizer. So for experiments, we used like multiple models, pre-trained models, monolingual and multilingual one, and we try them on different setups. So the baseline, we use a generic or conventional ASR pipeline. The acoustic model comprises of time-delayed neural network with LSTM, and it has a 4-gram language model trained on around 16 to 19 hours of data, and achieves around 17 word error rate. So for the models that we used, we leveraged pre-trained model, both the monolingual, there's like a base and a large model, and they're both pre-trained on around 4,500 hours of native Swedish data, and they achieve around like 32 and 22 respectively. We also try a multilingual model, which is this Wave2Vec2 XLSR, which is a group of data collection of common voice, Babel, and multilingual Libre speech, all of which has around 3 hours of Swedish only included in this multilingual dataset. And this one achieves around 28. So we also used even a larger multilingual model that was trained around, pre-trained on 100,000 hours of pre-trained data on a data set called Vox Populi, which is a Parliament European speech. And this one achieves around like 21, which is the best one. So we started to take our best model and incrementally increase the fine-tuning data from 5 hours to 16, and that achieves around, gives us like considerable outperformance. And finally, we just use the full fine-tuning data, 19 hours, and that gives us around like 14, which is the best. I'd like just to highlight that, you know, the baseline here is using language model and a pronunciation dictionary, while the self-supervised one doesn't use any of those. So just an acoustic model and an end-to-end strategy.
So while the word error rates do not always tell much about the real performance of the models, we also performed an error analysis in order to investigate what types of errors each of the models make. So in the first example, the student is most likely to ask about the opinion about Swedish royal family. The baseline model didn't successfully recognize the words Ansikt and Kungligen, since neither of them appeared in the training set. In contrast, our best model recognized these words almost correctly, with only one phoneme far away from the target transcription. In the second example, the baseline replaces the word tanker with tycker. While both of these words can be translated as to think, tanker refers to the actual thinking process, while tycker refers to having an opinion. So basically, in this example, the baseline replaces the word with the correct word choice and corrects the student's error. The student also didn't succeed to pronounce the word kanske, so he repeated the first segment of the word. However, the baseline system skips this repetition. In contrast, our model aims to produce the output as is, so it successfully produces the word tanker and the repetition kan. But due to the lack of language model, it fails to produce the word kanske and the following word Dragsvik, which is a name of a village in Finland. And finally, in the last example, neither of the models success to decode the word Joensuu, which is a name of a city in eastern Finland. The baseline system produces the output Järso, which means I am so in English. And our best system produces the output Jaenso. While the output of the baseline system makes sense grammatically, the output of our best system doesn't make any sense grammatically, but it's acoustically closer to the reference. So in our work, we demonstrated that the models pre-trained on large amounts of untranscribed native Swedish speech data can provide competitive performance of that to traditional hybrid HMM-based ASR systems. We also demonstrated that the models pre-trained on large amount of multilingual speech data are able to outperform the conventional systems when using only a small amount of transcribed data. Also, based on the error analysis, the self-supervised end-to-end acoustic models are more likely to produce the outputs as is, including student grammatical errors, mispronunciations, and disfluencies. In future work, we would like to investigate the effect of external language model in this end-to-end framework, or incorporate a decoding strategies such as beam search. The external language model is most likely to reduce the word error rate of the system, but it might be harmful in terms of automatic speaking assessment. For example, it can hide student errors, similar as the baseline did. We also already performed the fine-tuning procedure on language learners' Finnish data, and the results were promising. That concludes our presentation. If you have any questions, we will do our best to answer them. Thank you.
Let's thank the speakers. Questions?
So the solution, in fact, to introduce, in fact, this impaired pronunciation is to incorporate non-standard pronunciation which are possible, and of course to incorporate in your language model the possibility to have incorrect pronunciation. So what is your global policy? It's a bit faked, your comparison, because you don't have this possibility in the language model to have incorrect pronunciation. So of course, yeah, it's misleading. So what will be your policy, in fact, to cope with this L2 pronunciations?
Actually, one of the problems that we face, building customized pronunciation dictionary is not always like feasible, especially for like Finland Swedish. So I guess that requires some expertise to build up this. As far as our project is concerned, of course, we're planning probably to incorporate some of these, but it would be nice to see that the end-to-end strategy is actually helping us in this. So giving this faithful representation of what the students are saying is sort of kind of like helping us in this term. Hope that answers your question.
I think it's it's for pronunciation training. In fact, you have to cope with competitors. What are the possible competitors in one time? So you have to organize your pronunciation dictionary to cope with this. So what are the deviations which are authorized, which are meaningful, and what are pronunciation which are non-authorized or illicit? So it's a quite complex problem.
Yeah.
So we can discuss.
Yeah, I'd be happy to address that offline.
L2 and L1 training. Young children, fluency problem, for example, you cope with this problem for prosodic patterns. For example, you have licit or illicit prosodic pattern in the language. So you have to have some kind of a description of what is licit in a certain context.
Yeah, yeah, actually.
So you just have done a part of the role.
Yeah, I just would like to mention that this is probably the first part of the whole project. We just focus right now on the ASR component. The other ones, of course, are still in development. But yeah, thank you very much. Yeah.
We have a question online from Erfan Luemi, who asks if you could briefly explain the fine-tuning, and he asks in particular, what do you mean by fine-tuning the classification layer?
Okay, so basically you have, so the wave-to-vec model is just a transformer model, and it's already pre-trained on untranscribed speech that's in the pre-training mode. In the fine-tuning, what you do, you would actually freeze all the layers and keep only a last layer, just a classification layer, and you initialize that randomly, and you just train the system to predict the tokens, or like the graphemes in our case, the 35 tokens, you know, to produce the actual output. So it's just like a very straightforward discriminative. Yeah.
Thank you. I hope that answers your question, Erfan, but do feel free to follow up in the chat if you want to. Mm-hmm. We've got time for one more question, one or two more questions.
So maybe I missed from your presentation, but first of all, what is the age of the students, and if the data set is publicly available or can be available in future?
So basically all of them are high school students, which is around I think 13 to 15 years old. I'm not completely sure about if we are able to provide the metadata publicly available, but we are going to make the data set publicly available in Finnish language bank.
Thank you.
Another question from the room.
Hello. No, just wondering what is the units that you use to classify in the end, if it's the graphemes or the VPE, or what is the...
They're just regular graphemes, just regular characters.
Characters.
Yeah.
That's the final layer, let's say.
Yeah,
Okay.
just characters.
They are just characters, special tokens, and the empty symbol, which
Right.
is basic CTC.
And then also the test set is only 10 minutes.
Yes.
Yes.
Is it representative in that way? Like I would use maybe 1 hour, but...
Yeah, you're right. That's a very good point. We actually wanted to match the training and testing condition of another project we were doing in the research group, and we wanted to make sure that we have like some solid baseline for this. But you're absolutely right. Like increasing the data set would be a very sensible thing to do.
Thank you.
Thanks. I think that's all we have time for, so let's thank the speakers again.
Thank you very much.
Thank you.